intimidating.
Yeah, quantum computing.
Yeah, exactly.
Yeah.
But I think there's a really fascinating story here, and you want to really get into it. So welcome to the deep dive, everyone. This is like your crash course in all things quantum.
And you definitely don't need a PhD in physics to keep up. We're going to break down the whole history of quantum computing.
Exactly. So where do we even begin with something like this? It feels like every article I read is talking about qubits and entanglement and...
Well, it all starts not in some super futuristic lab,
Right.
but actually with a real challenge that scientists faced way back in the post-World War II era. They were making amazing progress with digital computing, but there was this problem. Simulating quantum mechanics on those computers was basically impossible.
Yeah, it's like using an abacus to predict the weather, right?
Yeah, totally different things.
Right.
So classical computers, they work with bits, which are tiny switches, either on or off, representing 1 or 0. But the quantum world, well, it works on completely different principles.
Okay.
Things can be in multiple states at once. It's called superposition.
Okay.
And particles can be linked together in this spooky way called entanglement. It's just not something you can easily represent with just ones and zeros.
Yeah.
Yeah.
So instead of trying to kind of force fit quantum problems onto these classical computers, some really smart people had this radical idea.
Mm-hmm.
What if we just built a computer based on the principles of quantum mechanics itself?
Exactly. And that is where the whole idea of quantum computing really began.
Yeah.
One of the first big steps on that path was in 1980 with this physicist, Paul Benioff.
Okay.
He introduced this idea of a quantum Turing machine.
Okay, hold on. I'm going to need a quick explainer on that.
Yeah.
What is a Turing machine and what does it have to do with this quantum world?
So imagine a theoretical machine
Okay.
that can read and write symbols on this infinitely long tape.
Okay.
Following a set of rules. That's a Turing machine, and it's the basis for all modern computing.
Got it.
Benioff essentially was what if we took the principles of quantum mechanics and applied them to this model?
Okay.
That meant that instead of just ones and zeros, you could have these qubits, quantum bits,
Right.
that could be in a superposition of both states at the same time.
Whoa.
Yeah, it's pretty wild.
So Benioff basically laid the theoretical groundwork for a computer that could tap into all the weirdness of the quantum world.
Exactly. He showed that a quantum computer wasn't just something out of Star Trek. It could be real, at least in theory.
Okay.
And with most groundbreaking ideas, it took a while for people to really see what it could do.
Right.
But in 1984, things started to get really interesting when Charles Bennett and Gilles Broussard came on the scene.
Okay, so what did they bring to this quantum party?
They introduced this idea of quantum cryptography, and specifically this concept called quantum key distribution. They proposed that you could use quantum mechanics to create encryption keys that were virtually unbreakable.
Okay, hold on. How does quantum mechanics actually make encryption more secure? I always thought codes were just complex math problems.
Well, traditional encryption, yeah, it does rely on mathematical complexity.
Right.
But quantum key distribution, it uses principles of quantum mechanics.
Yeah.
The fact that just observing a quantum system actually changes its state
Whoa.
to ensure that any attempt to eavesdrop on the key exchange would be detectable.
Oh, so if somebody tried to peek at the secret code, it would be setting off an alarm.
Exactly. Yeah.
Wow. That's really smart.
It's pretty cool.
Yeah. So it seems like security was one of the first major areas where people really saw how quantum principles could be used in the real world.
Absolutely. But the really big shock came a few years later with this mathematician named Peter Shor.
Okay. Yeah. Shor's algorithm seems to be a big turning point in all of this.
It was huge.
What's so groundbreaking about his discovery?
So in 1994, Shor unveiled this algorithm that could efficiently factor large numbers using a theoretical quantum computer.
Okay, so that sounds important, but why should the average person care about factoring big numbers? Sounds like something from high school math class.
Well, a lot of our online security,
Yeah.
from bank transactions to secure websites,
Right.
all of it relies on encryption systems that are basically based on the difficulty of factoring really, really large numbers.
Totally.
Yeah, it's called RSA encryption.
Hold on. So you're saying Shor's algorithm, if it was running on a powerful enough quantum computer, could crack the codes that protect all of our most sensitive information?
Pretty much. Yeah, that's exactly what sent shockwaves through the cybersecurity world.
That's kind of scary.
Yeah, it was a big wake-up call.
Yeah.
Suddenly, quantum computing wasn't just some academic thing. It had real-world implications for national security, finance, everything.
Oh, right.
But it wasn't all doom and gloom.
Okay.
There was a whole other side to this, the potential to solve really complex problems that were just beyond the reach of regular computers.
So it's not just about breaking codes.
No, not at all.
There are like all these other potential applications just waiting to be discovered.
Exactly. And that's what we'll get into in the next part of our deep dive.
Okay, so we talked about how quantum computing could break encryption, which is kind of scary. But you're also saying it can solve these like really complex problems.
Yeah, exactly.
Like what kind of problems are we talking about?
Think about the challenges we face in fields like medicine or materials science or even like artificial intelligence.
Right.
These often involve like understanding and manipulating things at the molecular or atomic level.
Mm-hmm.
Classical computers, they really struggle with this because the underlying rules are quantum mechanical.
So it's like you're trying to model the behavior of a flock of birds,
Yeah.
but you're only looking at each individual feather.
Yeah.
You're missing the bigger picture.
Exactly. You're missing the forest for the trees.
Right.
But quantum computers, with their ability to use superposition and entanglement, they could simulate these systems way more effectively.
Right.
Like imagine being able to design new drugs by actually simulating how they interact with specific proteins in the body,
Okay.
or even create like entirely new materials with properties we can't even imagine yet.
That sounds incredible. So are there like specific examples of algorithms that could make this possible?
Yeah, definitely.
I remember the sources mentioning something called Grover's algorithm.
Yeah. So Love Grover, he was a computer scientist,
Yep.
and he developed this algorithm back in 1996 for searching unsorted data.
Oh.
And this might sound kind of simple, but it has huge implications for things like searching databases, pattern recognition, even cracking passwords.
Oh, wow. So instead of having to go through a haystack, like one piece of straw at a time, Grover's algorithm lets you just like zoom in on the needle.
That's a great analogy, yeah. And then around the same time, there was another big breakthrough by physicist Seth Lloyd. He proved that quantum computers could actually efficiently simulate quantum systems.
Right.
Which is something classical computers can only do for very, very small systems.
So how does being able to simulate these quantum systems actually help with things like drug discovery?
Right.
Or material science?
Well, imagine being able to design a catalyst that speeds up a chemical reaction so we can have cleaner energy.
Okay.
Or simulate how proteins fold to understand diseases like Alzheimer's.
Wow.
These are problems that would take normal computers billions of years to solve.
Really?
But a quantum computer could potentially do it like way faster.
Okay, that all sounds super promising.
Yeah.
But let's be real here. Where are we right now in terms of actually building and using quantum computers? Are we all going to have quantum phones in our pockets next year?
No, not quite.
Oh.
Building and maintaining these machines is incredibly complex and expensive.
Right.
We're talking about manipulating individual atoms and photons, keeping them in this state of superposition long enough to actually do calculations. It's really, really delicate work.
So it's not as easy as just like slapping a quantum chip into our phones.
No, definitely not.
Okay.
It requires a completely different approach to computing,
Right.
a new way of thinking about algorithms and processing information.
Right.
And there are still tons of technical challenges before we see quantum computers everywhere.
So we're still in the early days, like the Wild West of quantum computing.
I like that analogy. Yeah.
Yeah. But even though it's early, it feels like one of those things that could totally change the world.
I agree.
Yeah.
And that brings us to some of the bigger questions that I saw in what you sent. Questions about what this all means for, like, how we understand reality.
Okay, now you've really got me interested. What do you mean by understanding of reality?
Well, think about it. If we can manipulate these qubits, which are like the basic units of quantum information, to do calculations and simulate reality, what does that tell us about information and the universe?
Whoa, that's getting pretty deep.
Yeah, it is.
Are we talking about like blurring the lines between the physical world and the digital world?
In a way, yeah.
Wow.
Quantum computing makes us think about some really deep questions.
Okay.
About the nature of reality, the limits of what computers can do, even what it means to know something.
This is starting to feel more like a philosophy discussion than a tech deep dive.
And that's what makes this whole field so fascinating.
Right.
It's not just about building faster computers, it's about understanding the universe and our place in it.
Yeah, my mind is officially blown.
It's pretty mind-blowing stuff.
But before we get lost in all the philosophy, can we bring it back down to earth for a minute?
Sure.
What are the next steps? What needs to happen to make this technology really work?
Okay, so we've established that quantum computing is super complex
Yeah.
and has the potential to change, like, everything.
Right.
So what are the next steps in this whole quantum journey? Like,
Yeah.
what needs to happen to make this technology actually reach its full potential?
Well, the stuff you sent me highlighted a few key areas.
Okay. First, there's this challenge of scaling up.
Mm-hmm.
Right now, the quantum computers we have like a few dozen or maybe 100 qubits.
Right.
But to really tackle the big problems like simulating complex molecules or breaking encryption, we need systems with like thousands or even millions of
So it's
qubits.
like a numbers game.
Kind of, but
More qubits equals more power.
it's not quite that simple.
Okay.
It's not just about having more qubits, it's about making them more stable and getting rid of errors.
Mm-hmm.
Qubits are super sensitive to their environment,
Yeah.
and keeping them in their quantum states is one of the biggest challenges.
That makes sense. It's like trying to build a house of cards in a hurricane. They
Exactly.
need a really solid base.
Yeah, and along with those hardware advancements, we also need like a software and algorithm revolution.
Okay.
We need new programming languages and totally new ways of thinking about computation.
So it's not just about the physicists and engineers building the hardware. It's also about mathematicians and computer scientists figuring out how to program these things.
Absolutely. And the third area is accessibility.
Okay.
Right now, quantum computing is mostly limited to labs and universities.
Right.
For this technology to really make a difference, it needs to be accessible to more people.
So we need like a quantum version of the personal computer revolution,
Exactly.
where computers went from these big, mysterious machines to something everyone could use.
Yeah, that means developing things like cloud-based platforms,
Okay.
simpler user interfaces, and educational resources to help people understand this stuff.
So imagine a future where anyone with an internet connection could use quantum computing to solve problems.
Exactly.
That's pretty exciting.
It is.
Okay, so it sounds like we have a lot of work to do,
We do.
but the payoff could be huge.
It really could.
Any final thoughts for our listeners as they continue learning about quantum computing?
One thing that really hit me while reading through all this stuff is that we're really just at the beginning of this whole quantum thing. There's so much we don't know and so much more to discover, and that's what makes it so cool.
It's like we're standing on the edge of this giant uncharted territory, and we finally got the tools to start exploring.
Exactly. And who knows what we'll find.
Yeah, who knows what amazing breakthroughs are waiting for us out there.
Right. And if these quantum computers can blur the lines between reality and simulation, what does that mean for consciousness? Could we one day simulate the human brain? Or even create AI that's smarter than us? These are some pretty big questions we'll need to think about.
Whoa, that's definitely something to think about. Thanks for taking us on this deep dive into quantum computing.
You're welcome. It was my pleasure.
It's been an amazing journey, and I feel like we've only scratched the surface.
Yeah, the journey's just getting started, and who knows what incredible discoveries are ahead.
I can't wait to find out. Thanks for listening, everyone.